Hello, and welcome back to another episode of Who Wants to Be a Millionaire. So if you remember last lesson, or the last video rather, I was talking about why when you differentiate something, for example, y equals 2x, or 2x squared, we'll have a little bit more interesting. When we differentiate something like that, or find the gradient function, basically, that's what differentiation does. When I do that, I end up with and so remember, you multiply the power by the coefficient, so you get 2 times 2 is 4. The power decreases by 1, so you're left with 4x to the 1, or just 4x. So what I want to do in this video is just talk about why that works. Why do we decrease the power by 1? Why not 5? Why not 1.2? Why not pi? And also, why do we multiply by that? So hopefully by the end of it, you'll see a bit of a connection there. So we'll start off by drawing a diagram. I'll try to draw that curve. It won't be the best because I'm not an artist. Something like that. Alright, this is my x, this is my y. And of course, I can write y equals 2x squared if I want, because that's the curve I'm representing. And of course, a common notation is f of x. I'll be using f of x here, just to get this machinery that we're going to need to work out the derivative. So if I start off by choosing, say, this point here, let's say the x coordinate there is just x, we'll keep it simple. Now, we could describe the corresponding y coordinate by any of these three. We could say it's 2x squared, so I could write 2x squared there if I wanted to. I could write y, or I could use this name f of x. And that's the one I'm going to try and use. I'm going to use f of x, and you'll see why I'm preferring to use the name f of x. I'm going to choose another point further up here, because what I want to do, remember when we differentiate, we want to work out the gradient of the tangent at that particular point. So what I'm looking for is the gradient of this line here, because if I want the gradient at the point x, I want the gradient of the tangent line at the point x. So what I'm going to do is I'm going to choose a point, say, up here. And now I could use x2 or another name for it. What I'll use instead is I'll kind of use the name x here, but I'll add on some amount here. I'll say I've moved h in the right direction. H for height, or h for Hussein, or whatever you want. So let's move that across by h spaces. We'll say that this has an x coordinate of x plus h. Now, if the height of this point was f of that number there, x, f of x, and the height of this, by the same logic, is just going to be f of whatever that x value was, so x plus h. So that's going to be the height of that point there. Or in other words, I'll just draw another quick diagram here. If I wanted, so this was 2x squared as well. If I wanted the height at the point x equals 5, where y, or f of x rather, was 2x squared, if I wanted the height where x was 5, I would simply substitute in there 5. So I'll be looking for f of 5, which would be 2 times by 5 squared, and that would be 50. So the height there would be 50. Or alternatively, I could just call it f of 5. And so that's basically what I'm doing there, but with algebra, because we want to prove it algebraically, to generally prove it, rather than just with all the different numbers. Because with proofs, you want to do it algebraically. You want to prove it generally speaking. And I know it's not a full proof in the sense that, well, I've only chosen the function 2x squared. I want to prove it for every single type of function, but I might leave that for a later video. But let's just continue with this, and we'll hopefully see that we do very systematically end up with this same function 4x. Right, so we've got that. Now, when I'm looking for the gradient function, if I want to get the gradient of this line here, why don't I start with a decent-ish approximation? So I'll start off by looking at the gradient of this line here that I've sort of put together somehow using these two coordinates. So I'll say that my sort of approximation for the gradient, we'll call it m, it's going to be the rise over run, isn't it? So if you remember from GCSE, it's just y2 minus y1 divided by x2 minus x1. And I'll choose this to be my second coordinate, so that can be coordinate number 2, and this can be coordinate number 1. So I'm going to do the second y coordinate, which is f of x plus h, take away the first y coordinate, which is f of x. So that's going to be f of x plus h minus f of x at the top. And at the bottom, I'm just going to find the difference between the second x coordinate and the first x coordinate. And the difference there is obviously an h, because if that's x and that's x plus h, then I've added on h, so the difference is h. Or if you want to rigorously see it, you could say that the second x coordinate is x plus h, the first x coordinate is x, and so you can see that that will just cancel, and I'm left with the fact that an approximation for the gradient in terms of x's and h's would be this expression here. That represents an approximation to the gradient. And then what you'll notice is that if I want to make, so if I choose, say, this coordinate here, so if I choose a coordinate whereby the h is a little bit smaller, you'll notice that I get a different gradient, and the gradient is actually a better approximation. So if I do this now, not the best dash line in the world, but the best we can do, you'll notice that as I make this h smaller, so if I make this coordinate come down here somewhere along this line, get closer and closer and closer to this coordinate here, you notice that I get this green line here, which is a better approximation to the actual gradient that I want, which is this one here. And so that's the idea basically, and we call this idea first principles. I'll just write that here, first principle, because it sort of breaks it down into its very basic components. It goes back to basics in a sense. So what we're going to try and do is use some sort of mechanism to show that as I make this h value smaller and smaller, as I make this x plus h get to around here, I get a better and better approximation. That's this whole idea of first principles. Right, so how we're going to make that happen is we're going to say that dy by dx, or more commonly referred to as f dash of x, it's now going to be similar to this. So the gradient function, i.e. this line here, it's going to be very, very closely related to this thing here. It's going to be f of x plus h minus f of x over this h. But the only thing that we need to ensure that happens is that this h has to be getting smaller and smaller. And to make that happen, we use this little thing here, and it says we want the limit of this as h gets smaller and smaller and smaller. And you might see that as a bit of a problem, because if h is the denominator and it's getting really, really small, really close to 0, then this whole thing might blow up to infinity. But what tends to happen is that in this thing here, you get, when you sort of simplify this with whichever function you have, when you simplify that, you do end up with the h's cancelling, so you don't actually have to divide by something that's 0. So let's do that then. This is very, very important, so try and you do have to remember this, and you do have to use this idea to work out the derivative sometimes, depending on what the question asks for. So a lot of the time you'll just get away with, when they ask you to differentiate something, you'll just be allowed to just multiply the power by the coefficient and so on and so forth. But if they ask you to show it by, or they might say show that the derivative of 2x squared is 4x using first principles, they might ask you to do that. If they ask you to do that, then you do have to follow this process here, and I'll just quickly show you now, because the video is getting a bit long, how you do that. So if f of x, we'll call this f of x, remember, if f of x equals 2x squared, then I really just need to work out the derivative. That means the first derivative, sorry, not the second. I just need to use this expression here and start substituting things in and see what happens, how I can sort of simplify that into something nicer. So f dash of x is going to be the limit as h tends towards 0. F of x plus h, what the heck is that going to be? Well, f of x plus h, if you remember over here, all we did was we took this, well, something slightly different that we did there, but same idea applies. I'm going to substitute all of this x plus h as the input for this function. So it's going to be 2 lots of x plus h all squared like that. So I've replaced this x, i.e. this x and this x, with an x plus h. So I've got this now. So I'll put that in there as this thing here. I'm going to subtract this f of x, which is easy, it's just that. Divide that by h. Remember, this f dash of x is strictly for this function, for this particular example. Alright, so we've got that. And now I'm going to try and expand this bit, see what happens. Hopefully it simplifies into something nice. I expand that, I get 2x squared plus 4xh plus 2h squared minus this guy here over h. And you'll notice then that the 2x squareds are going to cancel, and then you'll notice that I can actually factorize an h out here, and that's really important because, as I mentioned, the h at the bottom cancels out with an h from the top. So I'm left with limit. I can factorize an h there. I'm not going to bother about taking out a 2, don't really care about that at the minute. 4x plus 2h divided by h. That can go away with this guy. Limit as h tends towards 0, 4x plus 2h. And at this point now, I can substitute in h equals 0. Over here, notice I couldn't substitute in h equals 0 because I would have had to divide by 0, and I don't want to be divided by 0 because that makes a big mess. But I can substitute in here now because I won't get a mess. And if I do that, I get 4x plus 0. Notice that the h tending towards 0 has no effect on the 4x, that can just sit there. But the 2h, if a h goes towards 0, then the 2h is going to go towards 0 because 2 times something that's getting really, really small is going to become a 0 as well. And so I'm left with exactly 4x. And so f dash of x equals 4x, and that's exactly what we said up here when we said that the derivative was 4x to the power of 1, or indeed just 4x. And that's it really. I will make another video on more examples like this using this first principles idea, but that's the end of the show. So goodbye, thank you, hope you enjoyed it.